working?
Yes, perfectly.
Okay, so good afternoon, everybody, and thank you, Tatiana, for the invitation to present this part of the webinar. To tell you the truth, when you asked me to present about the conclusions and the perspectives, I thought that I'm one of the lucky ones because I don't have to really prepare technical stuff to present. But once I started preparing the presentation, I was really hesitant about what the message I wanted to share. So I'm going to end up sharing some slides in which I will express my view on how we reached the stage where we're using machine learning to solve our conventional geotechnical problems, and then maybe talk a little bit about the possibility of reaching a stage where we really get to benefit from the full power of AI in this discipline that we all love. So I will start with the rise of machine learning in geotechnics in 1 or 2 slides, then talk about the applications and capabilities, and then a couple of slides about challenges facing the ML in geotechnical practice. If we go back a little bit to the days of the traditional geotechnical engineering, we usually had a tripod, a triangle, which Professor Berland presented in 1987 in the way that you see here. So we have, the ground profile that we have to describe in the geotechnical problem, and that is the anchor point. This usually gets done using a site investigation. The traditional approach involves finding a simple ground profile that we will use later on to make decisions when it comes to geotechnical engineering problems. Step number 2 in the traditional approach, as you all know, involves testing, whether it's lab or field tests. And the idea here is to try to describe the behavior of the rocks or soils. And this usually requires some correlations, as you all know, from field tests or from laboratory tests. Once the soil properties are there, the final step is modeling. And again, going back to the days of Dr. Berland, 1987, when he presented this, modeling was about idealizing the problem, making it simple, either with the help of physical models or analytical models. Now, the whole trick in making a decision at the end of the day when it comes to design for geotechnical systems is to basically make a decision. And the way this happens is that you have to connect the 3 sides of the triangle through empiricism at that time, maybe experience and precedent, and eventually express some kind of risk management to make sure that whatever you're designing will perform. And in the old days, and even until now, the major risk management tool has been the factor of safety. So this is the traditional geotechnical approach. However, this approach has a lot of limitations, as we all know, and perhaps the word is uncertainty and variability. So in the 1980s, people in the geotechnical field figured out that going deterministic is not the way. So a lot of effort started to happen from a probabilistic perspective to try to improve the performance of the 3 sides of the triangle using probabilistic techniques. And I'm not going to go to the details, but that led to a lot of probabilistic work that aimed at improving the ground profile characterization, a lot of work that tried to quantify the uncertainty in soil properties, whether it's in transformation models or constitutive models. And finally, a lot of databases were used to try to characterize the uncertainty in our predictions, whether it's in the form of variable model factors or stochastic finite elements or response surfaces. At least now people believe that we need to quantify our problem in a probabilistic manner. Now, having described the 3 sides of the triangle in a probabilistic way, we still had to figure out how to reach the final product, which is, again, decision making. So the solution for that was the replacement of empirical approaches with some data-centric approaches, the replacement of experience with Bayesian updating, and the replacement of the factor of safety with more robust LRFD methods, reliability-based design methods, or quantitative risk assessment. So basically, that takes us from the 1980s all the way to maybe 10 years ago. This was the breakthrough that was done. Reliability-based design was the name of the game. But then for whatever reason, in the last 10 years, the improvement in this started to become slow. And the reason was that the geotechnical practice was not really embracing reliability-based design in everyday life. So us as researchers have been trying to improve and try to get this to practice as much as we can, but it seems that we are not succeeding. And there are design codes that try to implement the reliability-based design, but they have so many limitations that I'm not going to be talking about today. So what happened next? So in 2018, basically, digital disruption started to affect all engineering disciplines, especially in relation to machine learning, baby BIM, and digital twins. The Industry 4.0 technologies kicked in, as you know, with focus on smart automation, a lot of data, real-time data, and it seemed that the rules of the game started to be disrupted. And machine learning at that time emerged as a powerful tool that geotechnical engineers thought that can be used to probably push forward the reliability or the probabilistic approaches further and hopefully bring them into practice. Now, if we look from 2018 to now, there are so many researchers that have been working in this field. And today we saw samples of great work that has been tackling one of these three corners or more. But again, if we want to be practical, the number of practitioners who are now exploring and developing digital technologies, machine learning in practice remain to be a minority. And we have to be practical about that. And what's going to happen in the future, we don't know. Now, very quickly, I just want to show the progression of how we think about design since the 1940s until now. This is a graph that was put together by Professor Lacasse in the Rankine Lecture 2015. So again, very quickly, in the old days, we used to rely on in situ testing, laboratory testing, and analytical solutions to try to design our structures. With the advancement of technology, we were able to use numerical modeling to replace some of the analytical solutions. If you look at this blue line, this is where reliability-based design came into play, approximately in the 1980s. So if you fast forward 40 years, reliability-based design was only capable of taking a fraction of what we could do when it comes to design. So as I said, practice is not yet there when it comes to this technology, which is even older than machine learning. Now, if we look at machine learning and we come to our days right now, one would like to contrast between the impact of machine learning and the impact of reliability-based design. And the main difference, in my opinion, is the speed at which machine learning has moved and probably the speed at which it will continue to move. And just to give you a fun fact, the famous journal Computers and Geotechnics in 2018 did not accept papers that were based on neural networks and fuzzy logic. Professor Von Griffith, who was the editor in one of the meetings in 2018 in the United States, in one of the conferences, mentioned this explicitly. He said, we are not accepting papers that are based on the technologies or tools that we cannot explain. Now, fast forward 6 years, we have now a new journal, both of them, by the way, by Elsevier, that is dedicated to geodata and AI. This is a new journal that you probably have heard of, and which is having an editor, Professor K.K. Poon. So the speed at which things changed is expected to continue, and hopefully machine learning will not reach the stage where reliability-based design stopped. So for 40 years, we couldn't move further than this. I think machine learning might have a better way forward. Now, let's look at the applications in which machine learning have been used so far. So if you link those applications to the Berlin Triangle, we can see that site characterization is taking a big impact. Many projects are working on site characterization in ML. Geomaterial behavior, which is the other side of the triangle, is taking a chunk. And the last chunk is taken by actual predictions and design of actual geotechnical structures. So it is clear in this figure that machine learning is trying to tackle the three corners of the Berlin Triangle. Now, will it actually be able to pass the barrier of reliability-based design? Professor Foon, in one of his papers, argues that for machine learning in geotechnics to really move forward, it should involve the integration of information, data, techniques, tools, perspective, concepts, or theories from geotechnical engineering and machine learning. So what he's trying to say is that if we continue to work on the three sides of the triangle alone, we will probably not be able to do a breakthrough. We need to reach a stage where we have a super geotechnical engineer that is powered by AI and that is capable of learning and continuing to learn. Most importantly, not from data that is site-specific, but from data that has been pooled by experiences of all human geotechnical engineers around the world. And this is really something that is deep. So the super geotechnical engineer has to be capable of detecting site differences through data-driven model. So it has to be smart enough to know the site compared to other sites in the world. It has to be capable of making better site-specific predictions by drawing upon relevant past human experience. So we need to take that into consideration, and not only data that's coming from experimentation or investigation or testing. So we have to rely on the past human experience and try to get it into the mix. And finally, we have to be able to also merge between the power of machine learning and the machine learning algorithms and the physical and numerical expertise that we have in decision making. So to just list these again in one slide, and this is just for the completeness, if you wish, the main challenge facing machine learning right now is that insufficient attention is being given to the distinctive geotechnical challenges. Geotechnical engineering is different than any other discipline. And what makes it different is the connectivity between what you're seeing here in the slide. We have the geology with its variability. We have the geomaterials with their variability. We have the different methods that we use to make decisions, testing, monitoring, construction. And finally, more importantly, the objectives. We have these different design goals, risk management technologies, and again, the role of human judgment. If we want to have a powerful machine learning solution that the average practicing engineer will use in the future, we need to have deep appreciation for this geotechnical context. And if I want to summarize all this in one slide for the sake of time, I would go back to the Berlin Triangle and try to see if we continue to work on machine learning solutions for each side of the triangle alone. So ML for ground profiles, ML for soil properties, and ML for prediction. And by the way, today we saw examples of all these three. I am of the opinion that we will not be able to do the breakthrough in terms of practical decision-making in everyday practice. In my opinion, if we want to do that, and if we want to do the breakthrough, we have to find a way in which we tackle the problem as a holistic approach. How will it be done? I'm not sure. Will it be done in the next 5 years? I think so, because of the speed in which things are moving. To me, the final product for what we are all working on right now in ML is something similar to what we're seeing in ChatGPT right now, but for a geotechnical application. You go inside, you write what you have, you give the AI the information about your site, and that will not be the only input to the software or to the algorithm. It will basically rely on all similar projects in the world based on previous human experiences and based on the limited data, and try to give you answers that hopefully will be the solution. So with that, I will close and will be happy to take any questions.
Thank you very much. Thank you very much, Professor Najjar. Do we have questions in the chat? I think due to the time, we're going to pass directly to the conclusions. So thank you to all our speakers for sharing their expertise and for their insightful presentations. Thank you to all participants who joined us today. We hope you find today's session valuable and inspiring. A reminder that this session has been recorded and the video will be available on the CFMS YouTube channel by the end of the year. For those who would like to stay connected or receive an email when the recording is available, please be sure to fill out the form linked in the chat. Have a great evening, and we look forward to seeing you at future CFMS webinars. Thank you, everyone.
Thank you very much.